Python is going on, is it?
It's supposed to finish at 8, but it's still going on.
Okay, fine, no worries. We will wait for a few more minutes. Meanwhile, tell me, how was quiz one?
Good, sir.
Good. जो भी आपने सुना है stats 2 के बारे में, does it match or does it contradict?
The good thing is that whatever you revised on that day, so that was quite helpful.
Oh.
So credit goes to you also, and we expect that the trend will continue for quiz 2 and quiz 3 also, sir.
See, we just discussed what we had to discuss, and ultimately you should do, right? Quiz के सामने जाके, I am not doing it, you are doing it.
But that session was quite helpful, sir. And
Okay. लेकिन मैं ये नहीं पूछा था. मैंने ये पूछा था,
it
आपने
went well.
जो कुछ सुन के आया है stats 2 के बारे में, does it matching or it is contradicting thing? मतलब बहुत कुछ सुन के आया होगा ना stats 2 में, like it will be the difficult subject, you cannot do anything.
No, sir. Like, yeah, we heard like it is difficult, but any of the quiz can be tricky, sir. So, okay, quiz one was okay, is okay. So we expect like next maybe will be difficult, sir.
Okay, there will be
Difficult, but many people have just like exaggerated it too much. It is not that difficult. Like
No. I'm just joking. Actually, I'm not saying. I'm just joking. So, like people, they made some kind of environment like it's very difficult. You cannot crack it. But any of the quiz can be, the tricky, because when I was giving exam, right? So the beside me, the person, I think she already, last time she attended the stats and she couldn't clear. So that time before exam only, she gave me so much heads up, so I was scared. Okay, what's going to come in the quiz one actually?
Okay, there is one saying called expect the worst and you go, something like that. In Telugu and Tamil we have one good saying. So I cannot convert it to English. Like you should expect the worst and you should go.
Prepare for the best, sir.
Huh?
Expect the worst and prepare for the worst and expect the best.
Yeah. Prepare for the worst. You will get the best out of it. Something like that. Okay.
But sir, I will not say that what people are saying about the toughness and all. Of course, it all depends on what kind of background you are having and what kind of focus you are giving. But now I think the week 7 content is also released, right? So one thing I can say that both stats 1 and stats 2 have been so far the well structured and well executed course so far, sir. I'm not saying that other courses are bad; they're also doing equally great, sir. But the kind of linkage and continuity, getting reflected in both stats and stats 2, that is really commendable. It's my personal opinion.
Yeah. Even we like that connection between stats and stats 2. Right? Yeah.
So actually, just have one doubt or clarification. In the week 6, we have multivariable or integration for statistics, right?
Stats 2 में?
Yes.
Multivariable? Multivariable means we have two variables.
Two variables, yes, that's what he's saying.
But that part is still not covered in mathematics.
Multivariable? Oh.
He's saying double integration and all. That's what he's trying to say.
Double integration.
Double integration is not hard. You don't need.
Yes, but Gajaranji is not that hard.
It is not hard, but like
yes,
it's been so long since 12th, so we have forgotten.
Yeah. Even we do know that you don't know integration. So see, integration is basically continuous sum. That's how you should understand. In this particular stats too, whatever you are doing as integrate means you are actually continuously summing all the values.
Sir, since we are discussing next to course and all, I want to ask something, sir. Like week 7 content is released, sir, and we can see that there are only 4 videos in week 7, sir. Whereas in YouTube there are 6 to 8 videos for week 7. So have you redistributed or what, sir?
Yes. So week 7, week 8, we split those 2 weeks into 3 weeks. So now you are going to see week 7, 8, 9 as previous week 7 and 8.
Okay. And then what about real 9 and 10?
9 and 10 will be pushed to 10 and 11. 11 will be pushed to 12.
Okay. But no compromise on content, right?
No. We didn't reduce content,
Correct.
but we actually put some outlier content as additional content. We are not going to.
But by doing
focus
so,
on
sir,
that.
we are losing some activity questions also, right, sir? We are losing some activity.
Not much. See, even you
Okay.
get the activity questions also. But
Okay.
what we say and what we do is like we don't focus much on it, even on quizzes or to the end term. The students who wanted to learn can go through those lectures, all those activities can learn.
And just to a follow-up question to this, sir. So while we were hearing so much from about stats 2 and all, so somewhere I have made a perception that we will be discussing some advanced concept also, like ANOVA and all, right? And multi ANOVA and all. But that kind of content is not visual. So are we not going to cover certain in stats 2?
No. We are not going. We are going to cover only this
Hypothesis testing.
Hypothesis testing. Yes.
When that will be covered, sir? Those parts?
Those are advanced statistics. Okay, if this particular course converts to BS and if it is like 4 years, then you might have it in the 4th year or the 3rd year.
Okay. So those concepts will not appear even in the diploma and degree level also, right?
No, you don't require those things as of now in the diploma.
We don't require.
Yeah. Okay. We got some 34.
Sir, one more thing, sir. Sorry to interrupt you here, sir. Do you recommend any kind of books for the stats too, sir? Like
already there is a book, right?
Okay, that is given in the course of duration, right?
Yeah. Course
sir,
of duration.
For mathematical part, we listen about a book called Kapoor and Gupta. How is that book, sir? Gupta and Kapoor, something like that.
I haven't came across that.
Okay, no problem, sir.
Okay. Is Python session still going on?
Yes, actually.
See, today I have 4 concepts to cover. See, week 6 is actually, initially it was like a break week. What we did is we just split week 5 into week 5 and 6. So we have only very less to cover. Like
but this is helpful, sir. Load is distributed. This is helpful, sir. Yes, sir. So we have 4 concepts, sir. Kindly, we are relying heavily on you, sir.
Okay. Is my screen visible?
Yes, sir.
Okay. So these are the 4. I don't say these are difficult concepts. You have gone through these concepts in discrete case. Right now, today we will discuss the continuous case. That is the difference will happen. We will also see what actually the difference is. We will link it discrete and
sir, if time permits, sir, if you can include the function part also, then it will be a great help, sir. Because till now what I have seen, for me the function part is bit tricky. Be it discrete variable or be it continuous. Like functions of a random variable, be it discrete or be it continuous. Though functions we have covered in week 5, sir. But a little bit if you can throw some insight, right?
Okay, functions like y, any new random variable following some other random variable.
Correct. So for example, y is a function of xz plus x. Now x and z are my random.
Yeah. See, today's session I will start with this 4 concepts. I hope I will complete in 1.5 hour.
Yes, sir. Yes.
And I will take extra 1 hour, another 1 hour to go back. Okay, to week 5.
Yes, for functions, sir.
Week 5 we will go to quiz 1 syllabus, like weeks 1 to 4.
Okay, sir.
And one request from all of you is like, agar maine kahi pe, if I got struck, don't laugh at me. Okay, you just help me.
No, sir, we are relying on you.
No issue, sir. We never do so, sir.
Yes, we never do this with any.
I'm just kidding. So some might be like, "Arey isko ye bhi nahi aata." So even I am also a human. I will also make mistakes. And
sir, we are also sir Indian, sir. We respect our teachers, sir.
Yes,
sir.
Very well said. Yes, very well said.
Yeah. So you teach me, I teach you. So both ways we will improve our knowledge. That is what our main goal.
How are we going to proceed? By week 5th or week 6th initially?
Week 6. We will deal with these 4 topics. If we require
Okay.
some knowledge of week 5, we will just go back quickly and just revise that week 5 topics and just come back to week 6. I don't think it is required. I will try not to bring all those weeks. Without that, I will try to explain. Okay.
Yes, sir. Yes.
Sure, sir. Thank you, sir.
Thank you, sir.
Okay. And yeah, main today my session will be mostly on the intuition of joint probability density function. So what exactly this joint PDF means in physical sense. Okay, so I will more focus on it, and rest of the things will follow once you understand that computing this marginal density, independence, conditional density, this is all same in whatever we did in discrete case. Okay, shall we start? But I see only less crowd. Is this the crowd we have?
Sir, we can start, sir.
No, not like that. See, some might be interested to come. See, I am just asking: is 38 around 40 is the crowd we have every session, or is it more than this?
Today's less actually, sir. People might not be aware of the session probably, sir, because yesterday was a deadline, right? So they might not be aware of the today's session, sir.
Okay, and I can see even Python is still going.
Yeah, Python is still going on, so a lot of people might also be there. So there's that.
Okay, we will then start slowly. Okay, we'll start slowly. Meanwhile, they will start coming into the session. Okay, I'm audible clearly, right? Like louder.
Yes, sir. Yes,
Yes, sir.
Increase my voice or
You're audible, sir.
fine. Okay, fine. Okay, in week 6 we have mainly the jointly continuous random variables. Like we have seen in the discrete case, joint PMF of two random variables x. So even in this week we study about the continuous random variables. There are two cases mostly. One is like uniform distribution. So if both the random variables x and y uniformly distributed on a region, how will this jointly x and y probability density will be? And we will say other cases like non-uniform. If it is non-uniform, how will be the joint density of this two random variables? Like joint density and this jointly continuous random variables are actually what we get it from it is we actually find the probabilities of, so x will follow something, y will follow something. If they jointly combine, what will that follow and how are the probabilities will be, and these all things we will study here. And after that we will study the marginal densities, and later we will see the independence between two continuous random variables x and y, and finally we will see the conditional density.
Sir,
So yeah,
do the words joint and intersection, right?
joint
And intersection both mean the same thing or different?
Intersection,
Like sometimes we also call intersection probability, right? Like whenever we talk about joint probability, if you remember in our discrete classes, we make two sets, right? And we draw an overlapping part, right?
Correct.
And then we say that in order to find out the joint probability, they must have some intersections in common. So just I want to ask whether the word join and intersection mean the same thing or different?
Intersection will be between two events, okay?
Correct.
And this joint is between two random variables.
Yes.
Okay. So each one of it has their own terminologies, okay? Wherever you have to use that particular terminology in that particular sense. Like you say, in discrete case, you say range for any random variable, okay? In a discrete, if the random variable is discrete, then
we say range.
Yes.
But what values random variable takes?
So the values that random variable takes is called range.
Right.
But whereas in continuous case, we call it as support. We don't bring range into this.
Where probability is greater than 0.
So both means same, but their own, but the sense is different. Okay.
The context in which they are used, right?
So the same thing here also. That's density. Okay. So if it is continuous, we talk like densities.
Correct.
If it is discrete, we talk like mass.
EMF, yes.
Okay, like this. So there will be where you should use that particular terminology, you should use that those terminologies in that particular areas.
Okay.
Okay. Yeah.
Okay, sir. Yeah. We can move
Yes,
ahead,
sir.
sir.
Yeah. So we will start with by looking at what are the difference between the discrete case and the continuous case. Okay. So jointly continuous random variables means x and y here are continuous random variables, not the discrete. And the continuous case is more or less similar to discrete case, where in discrete case we talk like between the ranges. So range of x is something like tx, range of y is something like ty. The joint PMF of this will lie in the interval. This takes values tx cross ty, right? So here it is range, here it is in intervals. Okay. So for each x and y we have intervals. So do you know intervals? Of course,
Yes.
done maths on, right?
Yes, sir.
In discrete case, we call it as range. In continuous case, it becomes intervals. So between intervals, we will have the values. And here in discrete case, we dealt with PMF table. If you remember, we drew a table and we computed probability mass function, probabilities of each event, and we put it in a table. Here we will talk about joint PDF, which is called probability density function. Okay, there we studied joint PMF. In continuous random variable case, we study joint PDF. And if you wanted to find some, if you have some event and if it is some union of smaller events, what we do is, in order to compute the probabilities, we actually sum up them. But in continuous case, we actually integrate them. So we use integrals in place of sums. Okay, that is how that is the difference between discrete and continuous. These are the differences between discrete and continuous. Wherever you use summation, here we will use integral. Wherever you use PMF, here we will name it as PDF. Wherever you use the ranges, here we will use the intervals. So these are the basic differences between discrete and continuous. Rest all things are same. So however you compute there, here also we will compute in the same sense. Like if x takes values in AB, in the interval AB, and y takes values in the interval CD, then this joint distribution of xy takes values in the region A comma B cross C comma D. So you see, this is a graph of graph plotted on a Cartesian plane. So x-axis is like the values of x takes, y-axis is like the values that y takes. So in this interval we have x, and in this interval y values are, so y values takes in this interval and x values takes in this interval. But the joint distribution takes values in this region. So in this complete region, complete rectangle, it takes the values. Okay. So this is the
Yes.
combined region. Okay. If you combine it, we will get the region. If you look at separately, you will have intervals. So two intervals, if you combine, it will become a new region, and xy takes values in those regions. Okay, this is if you plot the graph of a joint, uh, so jointly continuous random variables. If you wanted to see the graph of where it takes the values, if I know the values of where x takes and y takes, this is how it will be. Now we discuss the important one, joint probability density function, which is, in short, we call it as joint PDF. So which we will use for continuous case. We just discussed, right? Joint PMF, here it will be joint PDF, which is joint probability density function. What this actually means? So this joint PDF of x and y is a function f of xy. It is a two variable function, that gives the probability density. So what this gives you is, it gives the probability density at point x comma y. So f of x comma y denotes, or the value of f of x comma y which you see in any question is actually the probability density at point x comma y. So tell me this, in physical sense, what is density?
Mass by volume, sir, like per unit volume, something like that.
Mass per unit volume.
Okay,
Mass by volume, yes.
Mass by volume, okay. There is another definition for density. What is population density? How do you compute population density in our India or some other places?
In a per square kilometer area, how much population is residing?
Yeah.
Correct.
The population in area
Per
square kilometer.
Yeah, in some area divided by that area.
Right? Divided by area.
So this is what density in physical sense. Here also the same thing. So this is actually the probability density. So what this means is, this actually means the probability that x comma y will be in a small rectangle. Okay, I cannot show you in the, let me zoom out a bit. So you see this graph. So we have x values takes between a and b, y values takes between c and d. So our xy takes, the joint xy takes values in the rectangle A, in this blue shaded region.
The A and B are the intervals now?
Yeah, AB is the interval for x and CD is the interval for y. So y takes in between CD, x takes in between AB. So the joint xy takes values in this rectangle, blue rectangle. Now, the probability that x comma y, so this joint x comma y, in this small rectangle with width dx and height dy around this point x comma y will be fxy times dxy. Okay, the probability density times the area. So the probability, actually, if you see here, this particular joint probability, okay, joint probability density is nothing but probability in that area divided by area. Okay, so probability in that area is actually something.
So can we write probability in that area upon total area?
Yeah, that we will see. Okay, right now this statement tells you is the probability that xy will take, the probability that xy will be in the such that this will be in this rectangle, dx dy will be fxy dot dx dy. So this is the probability in that area. Sir? Of that area. Yeah.
When we say probability in that area, so it means it includes both. It is the probability of x, y, or both. So how do we calculate?
Probability that joint xy. This is, we are talking about the joint xy. So the denotion of joint distribution is this. Open brackets xy is nothing but the joint distribution of xy, where x and y are continuous random variables. Okay. Okay. We are talking about the probability that this joint distribution of xy in this particular area, in this smaller area around this xy.
So just allow me to give some perspective around this while I'm asking this question.
Sure,
so you are asking, so since you are explaining so nicely, so I am not able to stop myself to ask this question. For the example, when we say probability of one random variable, right? So we say that in a number of favorable incidents or event by total number of events. It's a basic definition of probability, right? Now here x and y are joint, right?
Yeah, joint.
So what is the physical understanding of that? What is the intuitive understanding of that, sir?
So intuitive understanding is, see, this particular point tells me that x is taking value small x and y is taking small y. Okay. At this particular point. Like
just like discrete, but in this case it's just continuous. Is that it?
Right, correct. So in discrete, you can
Okay.
actually see the values, like you
We
can
need to
actually,
see x equal to 2, y equal to 3, something
yeah,
like
you can
that.
see that. But here, actually, between a, b, x can take any value, any real value. So it's like if a is something like 1 and b is something like 5, it can take 1.12 or 1.13, 1.14, 1.1234. X can take any value in between 1 to 5. Okay. Similarly, y can take any value in between c and d.
Right.
So when we wanted to talk about, if you wanted to combine both of them, so what happened in discrete case? So in discrete case, if your x can take some two values, y is taking some two values, how many different values can joint xy can take? So if you draw the table,
4 values.
Four values.
4 different boxes you will have. So what
Yes.
exactly is happening? This each and every x you will compute y, you will map it with y. Like that you will get 2 times 2, which is 4. Okay. So here also, in this particular interval times this interval, this will be the length and this will be the height. For every particular value, you will have particular y. You can map it to particular. So for a, you can have from c to d. The next point of a, you will again have from c to d. Y can take from c to d. Like this is built up with each and every point. Each point denotes x taking value x and y taking value y. Okay. It's this particular rectangle is made up of individual points, infinite points.
So
Okay.
when we say that joint probability of fxy, we are saying the probability that x is around the value capital X and y is around the value capital Y. Is that it?
That is not probability. That is probability density. That is the difference between probability and probability density. That is what I want to tell you. See,
What
joint
is rent?
probability density is actually probability divided by area.
Yes.
Yeah. Yes.
Okay. So probability is fxy dx dy.
Okay. So dx and dy are the small intervals.
Smaller intervals around xy. Smaller
Okay.
length and height of x, around that point xy. So you see, in continuous cases, for particular point the probability is 0. You cannot we cannot have probability values for each particular point. So that is why what we do is we look at around the area around, smaller area around that points, each and every points. Okay, we take that area, we divide that area by the whole area, you will get the probability, and that probability is nothing but fxy of dx dy. So that is how we define. From here we will get the joint density function, which is fxy. So this is the probability, and you divide it by area, you will get fxy. Okay, this particular fxy, what you are seeing in every example or in the lectures, this joint PMF fxy is actually the probability density, not the probability. So that is why the values can be greater than 1 sometimes. Okay.
Okay, sir.
It's not the probability, it's the probability density, which is the probability of that area divided by area. Okay, it can go more than 1, less than 1, but there are few properties of this fxy. It will always be greater than 0, and we will see that. But the physical sense is this. So fxy, this joint PDF is not the probability function. This is the probability density functions. Even in the one variable case also, you might have seen our PDFs, for some values it may take greater than one value, right?
How can it be,
Yes.
sir? Probability itself is less than 1 and you are dividing the area. The area is less than 1.
Area can be less than 1, right? You don't know that here the area is very small. Dx dy is like 0.010001 or something. Smaller.
Dx dy bigger square we are talking.
Bigger?
No, dx dy is inside a bigger square. Which area we are talking now? The smaller one or bigger one?
Smaller one.
Oh, okay.
So at the idea of bringing areas is because the probability at particular point for a continuous random variable will be 0. Okay. So if I ask you the probability that x takes small x and y takes small y, it is 0. It will be 0. And 0 divided by, if you wanted to see the
It is
density.
0 or some real number is there, which is an unmeasurable small number.
No.
We call that as 0.
It is 0.
0.
Yeah, 0. Okay. So if at each and every point it is 0, if you talk about the density, then you won't get anything. So the density is actually defined population density is like population divided by area. In the same way, probability density is probability in that area divided by area.
Per unit area.
Per unit area, or whatever the area we define.
Yeah.
The probability of that area divided by area will be the probability density, joint probability density. So therefore, the probability can be computed like this: fxy times some dx dy. If you multiply, that will be the probability at point xy, around point xy. Okay, this is the behind idea of this joint PDF.
Hello, sir.
Yeah.
So it's not necessary that in the joint PMF, joint probability density function in between 0 to 1. Not necessary, no?
Not necessary. It can be greater than 1.
On lesser than 0?
Lesser than 0, it cannot be.
Okay, sir.
Okay. See, densities, these are densities, okay. Can density be less than 0?
No. Never, sir. Area can never be less than 0.
Yeah, see, in physics or in 10th standards also we have seen densities are like mass by volume. Mass is mass is not negative, volume is not negative, density will be positive. Even in this case also, in other case densities also it is positive. Densities are always positive values.
Yes, sir.
Yes, sir.
Yeah. So
may I ask a question here?
Yeah.
When you're actually mentioning this, it's clear, but when the mathematical expression is coming, you're written it as f of xy into dx dy by dx dy. So normally the assumption is they can cancel out. Why is it that we can't cancel them out this time?
Why is it we cannot cancel?
Oh, you're able to cancel it out. So PDF is...
See,
okay.
See, I just wanted to just go back and just ask one simple but not easy question. When we do integrals, why we write dx?
Because
if I can try, I would say it is area under a curve if it is the curve that we're actually looking at, and I'm taking small strips dx and summing up the heights over a range of lower limit to the upper limit.
What is d? What exactly dx is here?
Dx is infinitesimally small. I'm actually the length. I would say I'm computing.
It is the length of the rectangles, a very small rectangle kind of thing.
Correct.
Along the x-axis.
So we actually divide any curve. We actually divide this curve very smaller rectangles. We actually sum it up. So whatever you divide, the length of those rectangles are dx. So dx is not something we just put it like that in the integral. Dx is actually you are actually computing the areas of rectangles, and integral is just summing all those rectangles. Okay, integral is not new thing. It is actually the continuous summation.
Summation of all the small rectangles
So
to create
that is why we write dx. Dx can be cancelled out. Dx is nothing but the length value or some value.
Sir?
Yeah.
As we said, and that's what we know also, that integration is just a summation, right? Like for discrete number we do summation, and for continuous number we integrate, right?
Integrate, yeah.
But sir, I'm not able to solve this puzzle, so I'm asking this. Like while we add number from 1 to 5, or you may say from 0 to 5, right? These are discrete numbers, right? So the summation is 15. If we add 5, 4, 3, 2, 1, it is 15, right? And quite obvious, there are many numbers. Say, for example, from 1 to 2, it will be 1.1, 1.2, 1.3, 1.4, right? But while I am integrating from 0 to 5, My answer comes 12.5, sir. Ideally, it should come more, na?
0 to 5, which thing you are integrating actually?
Your
dx,
function
sir.
is continuous.
Continuous,
Your
yes,
function that you're-
continuous number.
Hold on. Your function is continuous.
Right.
If your function is continuous, you are not going discrete numbers. Your function is varying from 1.2 to 1.02. 1.01 to 1.02 also it is varying.
Ravi,
So it is continuous.
Ravi, just a second. If we write it down, then things will be more clear. Sir, can you write down? Sign of integration?
Sir, I have a thing to say. Like, while this discussion is really very insightful, it's not forwarding us with this current, whatever you had in plan.
Mm-hmm.
Okay, we can proceed, sir, but we'll come back to this, sir.
Yeah,
This
we
is
will
very
come
much.
back. Okay.
This is very much related to the current discussion.
Yes,
also.
yes, of course,
yes,
of course.
Yes, sir. Okay, sir.
Okay, we will come back. Okay.
Yes.
But the idea of bringing a new term called joint probability density function is this. Okay.
Yes, sir.
Okay. We cannot directly compute probabilities at each point. So we introduced this area concept. Once area came in, we introduced this density concept into it, and we will talk about probability density, area, and probabilities with those. Okay. So yeah, let's look at the formal definition what in lectures discussed. So this particular joint density, which is actually f of xy, is said to be joint density function, joint probability density function for some random variables x and y, if there are two conditions. First condition is f of xy is always greater than or equal to
0.
0. So just now we discussed density should always be greater than 0, greater than or equal to 0. Either density is 0
Yes.
or it will be greater than 0. And so even the same thing we have, see, I just said summation should be replaced with integrals. So in discrete case, so if you add all the PMF, all the range values, if you add all those things, you should get 1, right? So if you sum over your PMF, you should get 1. Sum over along the range of x or some random variable, you should get 1. Or the PMF table, if you add all the PMF values, PMF table in that you have, whatever values you have in the PMF table, if you add all those, you should get 1. So similarly here also, we cannot write it out like a table form because these are continuous things. What we do is we sum it continuously. We sum it continuously means what we do is we integrate the density function along minus infinity to plus infinite and of x and minus infinity to plus infinity of y. So if you integrate it on whole r square means it's like r cross r. So if you integrate it on and whole, you should get 1. So this integration parts, you don't need functions of two variable difficult concepts. Here you just need, we will give you anyway, not a big thing, but you should at least learn some basics like what will be the integral of x, what will be the integral of maybe x square,
Yes.
x power n. So let's say x power integral x power n, what it will be, something like that. Very small value, small examples you must learn. Even if you don't learn, we will give you, you don't need to worry. So if these two conditions are satisfied by this particular f of xy, which is called density, probability density, if these two conditions are satisfied, then that probability density can be called as joint probability density function. Okay. So this is joint probability density function of some x and y. And if you have the joint probability density function between two random variables xy, we can actually define some events A, and we can ask the probability that xy, this joint probability belongs to some area A. What is the probability? So in order to compute these things, what we will do is we actually integrate it around that area A with the probability density function. So you just have to integrate this function fxy in this area. along this area. So you will get the probability that your joint distribution xy will belong to that particular area. So even like this, if you have this area, you wanted to compute the probability that xy belongs to this particular area A. See, if it is uniform, you can say you can just divide area by area. But if it is not uniform, what you do is you have to integrate along this A. That means you have to integrate from where x is going from to where, and from where y going to and that will become an area, and you have to integrate along that area. You will get the probability.
The limit of the integration was that
Limit of the integration, limits, huh?
yes, sir.
Yeah, limits you can write. See, if this is the area we are asking,
okay,
then the limits of x will be from here to here, from A to B, and limits of y will be here to here, from C to D. So
C to
I
D.
can write A, B, C, D like this. So limits integral, in integral you will always write the smaller value down and the bigger value.
Yes.
Okay.
Upper to lower.
Yeah.
Limit.
Yeah, limit will be upper to lower. And yeah, one other thing is like support of this joint distribution xy. So this support is nothing but all the points xy such that this particular fxy is greater
than 0.
Yeah. If your joint density function has value greater than 0, you collect all such points and put it in a set, and that will be the support of xy. And finally, yeah, this joint density of x and y will be represented as this fxy of x comma y. So this is the denotation you are seeing from the right from the stats to week 1.
Yes.
The same denotation we use for density function. Okay, yeah, and we will move to some cases of this joint PDF. If this joint PDF is uniform, if x and y are uniformly distributed, then we have some sort of joint density function. If it is not if it is non-uniform, we will see some example and we will just try to compute something. So we say xy, this particular x and y is uniformly distributed in the region D, which is in R square. R square is nothing but xy plane, R square. In that R square, a smaller region D, we say xy is uniform around this in this region D with total area with mod D, if they have joint density as 1 upon mod D in this region D and 0 otherwise. So why this became joint density? So in order to become joint density, it should follow two conditions, right? First thing is fxy of x comma y should be greater than or equal to 0. So you see in this region D, it is 1 by mod D. So area is actually positive. So 1 by some positive value is always positive. In this region, it is positive, and outside that region, it is 0. So it is actually, the first case is like it is satisfying the first case. It is either greater than 0 or it is 0. And the second thing is like if you integrate it on whole R square, this f of x, this particular 1 by mod D dx dy, you should get 1. So will we get 1?
Yes, sir.
Yeah, so this 1 by mod D doesn't depend on x and y. This is actually 1 by mod D. This is integral dx dy is actually the area of that region. It will give us the area of that region, and it will become mod D. And this will get cancelled, and it will become 1. So this satisfies both the conditions, and this will be the joint density for xy, where xy is uniformly distributed. Uniformly distributed means at each and every point the density is same. Okay, that is what it gives. It tells us also. Even this function tells you the same thing. So whatever x and y you take in the region, my density will be 1 by mod d only. It won't change. So the same density throughout the support. So throughout the support, you have the same density. That if you have the same density throughout, then we say x and y are uniformly distributed. What if the densities are different for different points? Then that falls into a non-uniform case. So something like if you have a joint probability, joint PDF as like this, something like this, where xy belongs to, what is this? So 0 comma 1 cross 0 comma 1 closed.
Limit
Interval of
Limit
x and
of
y.
x and y.
X and y. And this particular denotation is actually denoting the region. 0 1 cross 0 1 means it's actually the region, it's actually the unit square.
Unit square region.
Yeah, unit square region.
From 0 to 1.
Yeah, from 0 to 1, like this.
So here the first box belongs to x, right? And the second box belongs to
first
y.
block belongs to x and second block belongs to y. But this particular 0 1 cross 0 1 represents a region. Okay, region, this region. 0 1 0. So this region you can actually write it like this. So 0 1 cross 0 1 actually mean a region. Okay, if my xy is in this region, my value is like 4xy. My density value is like 4xy and 0 otherwise. First thing is like
4xy.
4xy. We have given you 4xy. It is given 4xy, but you have to cross check it. How do we cross check it? I claim that this is joint PDF, but you should not believe this. But you should check with conditions. So how do we check? First condition is your fxy
fxy greater than equal to 0.
So your xy values are positive values. So 4 times positive values will always be positive, and it is 0 otherwise. So do we have any points where density is negative?
No.
No.
So this is satisfied. Next thing is you have to integrate along, what are the limits?
0 1.
0 1 0 1.
0 1 0 1. fxy of xy dx dy. So it's like 0 1 0 1 4xy dx dy. So how do we integrate this?
First with respect to x.
This is
so
you take it as an x limit. So y is constant. You can just
4y.
bring y outside. So 0 1 4y. You can bring it out. 0 1 x dx dy. So integral 0 1 x dx will be, this is
x square
by 2, and the limits are from 1 0. So if you solve it, we will get
1 by 2.
Okay, this complete value will be 1 by 2.
1 by 2.
So this will be integral 0 to 1. So 1 by 2 times 4y will be 2y.
2y
dy.
And if you
dy.
integrate this,
Y
square by 2.
1 0
y square. 1.
So the second condition is also true. So if these two conditions are satisfied, then we can claim that this particular fxy is the joint PDF of random variables x and y which are continuous random. So yeah, there are some questions which relates to probability. We will come to that, and let's see something. Yeah, we will come to that. How do we compute the probabilities of some smaller events given to you, like some smaller events like not on the whole whole 0 1 and 0 1. What if it's like find the probability that is like x is greater than y, one random variable is greater than other random variable. Something like this. So if I ask you probability that, so this is an event, right? X greater than y is one event. So one random variable taking higher values than the other random variable is my event, and I just wanted to compute the probability of this particular event. How do I compute? How do I proceed actually?
You can write this as probability of x minus y greater than 0, right?
Okay.
Half into base into height. Yeah.
Okay. Let me discuss. So even if it is uniform or non-uniform, fine. But you have to see the region where you have to find the region of which this particular event is valid. Okay. So we have so let us say this is 0, 1 to 0, 1, 1 and 0. So this is the complete region. But what we require is in out of this complete region, what region actually represents this x greater than y. So in which region actually x values are greater than y values?
Half region.
Yeah. So if I divide this,
X equals to Y.
this is actually y is equals to x. This line is actually y is equals to x. So above this line, I can hear my voice. Okay. If you look at the above this line, if you take any random point and you see the x coordinate and y coordinate of that random point, so how what is the relation between those things? Like here you see it is 0, 1. So 1 is greater than 0, right? So whatever the point you choose, here the y value will be greater and x value will be smaller.
Okay, sir.
Right? And you see in this.
So we have been asked X greater than Y.
We have been asked the x greater than y. X greater than y will come in this region.
In this region.
Right? You don't need to check. You don't need to draw for the all region, but you just our complete region itself is 0, 1, 0, 1 square. So in this square, you just find what subpart actually satisfies this condition, x greater than y condition. So half of the region is actually x greater than y, and half of other region is actually x less than y. So now what will be the probability that x is greater than y?
The area of it, this image.
Area of
1/2 into
the
base
half
into
triangle
height.
divided by full square actually.
Sir, 1 minus area of shaded region, sir.
Area of triangle.
Half into base into height.
Half already.
Yes,
Just
sir,
half.
Okay.
Yeah, going by that logic, it's half. I'm just saying the formula.
But I say you guys are wrong. See,
Area
without
of triangle.
point PDF, how you are telling me? If it is uniform, your answers are correct. It is half. I agree. If it is non-uniform, see the thing.
Where
is,
unit are same.
Yeah. See the thing is, this densities actually gives you. If the density of this is greater than this, that actually tells that probability that x and y takes values here are more than here. So that is what density tells you. See, even I just wanted to link it with population only. If some area has higher population and some area has lower population, okay, the density of this population will be greater than the density of lower population, right? So you say there are 3 regions. Here there are some 15 people. Here there are some 4 people. Here there is only one person. Okay. This probability density is higher. Probability, density, population density is higher. This is greater. This is greater. Correct. The population density of this region is greater than this region, and this population density is greater than this region. What it tells you, actually the population here is more than here than here. Correct. Here also, if your probability density function value takes higher values in this region and lower values in this region, what actually that probability density function tells you is the values x and y takes these values are higher. There is a high chance probability that the x and y takes this value is more than here. So that is what density, probability density function gives you. If it is non-uniform, this 4xy, this particular 4xy is actually telling you that around 0, the density is small. If you keep on increasing your values x and y, so here the density is higher. Am I correct?
Okay.
4.01 times 0.1 is more, or 4.05 times 0.5 is more? This is more, right? This is 0.25. This is 0.0. Yeah, this is more. Okay. What this actually tells you is the density actually slowly increases, and here the density is very high. So at 1 it is 1 comma 1, it is actually
At
4
boundary,
with
it's very
density
high.
4. Yeah, here it is high, very high. Here it is somewhat low. Slowly it keeps on decreasing, and at 0 0 it is very nearer to 0. So the density is very low. So this is what it tells you. Probability density function tells you that the chance of x and y taking values around 1 is higher than the chance of values taking around 0. The chance is more at around 1 comma 1. That means the probability that x and y takes around 1 comma 1 is more when it compared to probability that x and y takes values nearer to 0 comma 0. Okay, that is what actual density tells you. This joint PDF tells you that if it is non-uniform, it tells you like this. So in some region the probability is high, some region the probability is low. So that is what non-uniform means. So the probability density is not same. That means if it is not same, the probability is not same. If the probabilities are not same, that tells you that the value that x takes, some values are have higher chances than the other values. Even in discrete case, same, right? If it is non-uniform, x and y takes 0 comma 1, let's say 0 has some 0.9 probability and 1 has some 0.1 probability. What this probabilities tells you, the chance of x taking value 0 is more than the chance of x taking value 1. So in discrete case that, in continuous case this. Density actually tells you in which interval or in which region the probability is high. The x takes values are high. So that is the
One
so
question
here if I say it is uniform, then whatever the answers you gave, like half, whatever, is true.
So, but in this we can't say if it is uniform or not.
Yeah,
We
in this
have
I didn't mention. Let's say it is
yeah, not mentioned.
non-uniform. It is non-uniform now. If it is uniform, it is easy to understand, right? If it is uniform, it is easy case. Just find the area of that particular region you require, divide it by total area. So
one question here. Won't that non-uniformity of distribution be covered by the function itself?
What is? I didn't get it.
When you say non-uniform distribution of density over the area, that is something which is covered by the function itself, isn't it? How would the distribution varies over the area is covered by the function, correct?
This particular function. You are talking about this function, right? This
correct. Function fxy.
Yeah, function fxy gives you actually the densities. From that function fxy, you can actually find in which region the probabilities are high, which region the probabilities are low. For 4xy, it will be like this, whatever I drew. Like this.
Okay.
If the function is different, the densities will vary.
Okay. Right.
Depending upon the function, it is whatever you said is correct. Depending upon the function, the densities vary.
Okay.
Values are changing at x-axis and Latin that is changing in x-axis, and y-axis is defining the density of that function.
Now let's say the density function is 4xy in the interval 0 1, in this region 0 1 cross 0 1 and 0 otherwise. So if this is the PDF, Now tell me, what is the probability that x takes higher values than y? So this is an event. For an event, I said you have to integrate along this area.
So can you please repeat the question one more time?
So what is the probability that x is greater than y if the joint PDF is 4xy in this interval 0, 1, in this region 0, 1 cross 0, 1? So okay, I'll simplify your question. So probability that x is greater than y is around this event, you have to integrate. So just give me the limits of this particular event. So you have to integrate your density function. So if whatever, that is the thing we discussed, right? Even in above, if some smaller event, if I ask you the probability of some smaller event, you will integrate you will integrate
something like 0 to 1 minus x from
x 0 to 1 and
1
y
minus x.
1 to 0.
y
1 to 0.
0 to 1.
Okay, you can do it in two ways. You can write these limits in two ways, but one way I prefer, write the x limits first. So in this region, x can take from 0 to 1. So in this particular region, x can either take 0 or x can also take 1, and x can take any value in between 0 to 1. So the limits of x will be 0 to 1. So now,
So just a second, isn't that the
Why?
limit for
Why?
the
No,
y?
no. X will be inside.
it's not. Okay.
Okay.
Because
dy
that will.
dx.
So it does not matter which integration we are doing first, right? Okay, okay, okay then.
First we
I
can
can
integrate
take it
with y
inside and
and
I
then
can
x
take it
also.
out. Okay. So okay, 0 to 1 is the limit for x. So once you fix the limit for x, now tell me what is the limit for y?
0 to 1 minus x.
0
1 minus
to y.
0 to 1 minus x.
0 to x.
0 to
1 minus x.
No, but it depends on how the equation of the line is
0
stamped.
to x, yes, 0 to
1 minus x.
Y is equals to x.
Y is equal to x means like, if I do it completely from 0 to 1, it will compute the entire square. We only need the bottom half of it.
No, region is defined as 0 to 1, 0 to 1.
A region is defined.
Yes.
But the total region I don't require, right? I require the region of x greater than y. So how do we find this? See, x takes values from 0 to 1. So for each particular value, y will vary from, so y
0
will
to
be
x.
very different.
0 to x.
Yeah. So here if I take x value is this, y will vary from here to here. It won't go beyond this. If I take here some value, y will vary from here to here, which is greater than here. Correct?
Yes.
So y actually takes whatever the value. If I take some x here, with respect to this x, y takes from 0 to
x.
This value x.
Okay.
Correct? This particular value. So from here to here. So what I will do is, see, this is nothing but we are just summing up. Okay. These integrals are summations. So x, you know, right? I from how to sum two summations. I is equals to 0 to some infinity. J is equals to 0 to infinity. For each I, you just sum over from 0 to infinity. Here also the same thing we do. For each x, you first integrate from 0 to x, and you will integrate along 0 to 1, over 0 to 1.
Sir, might be a very trivial doubt, but when my y equal to x, right? So then this x is greater than y. This is a little bit challenging to comprehend.
X greater than y, is it?
Yes, yes, because when my y is equal to x, right? And here also while integrating, we are taking, if my x is say for example half, then y is also half, right? If x is 1/4, then y is also 1/4, right?
X is 1/4 then?
While I'm deciding the limits, like these 2 points which you have drawn, that x can take any value from 0 to 1, right?
X can
On the
take
horizontal axis, right? Then we are saying that, say for example, any point in between. So whatever is the value of my x, that is the value of y, right? Because y equal to x, this is the line, right? So then how come x is greater than y? This, I'm not able to visualize.
That region where the sir has given the shaded portion, that region is covered by x greater than y.
See, whatever the point you take in this particular region,
at that region,
you
x will
just
be
take
greater than
randomly
y.
one point.
Right.
So this point has x coordinate greater than 0. X coordinate value is higher than the y.
Yes, true. Yes, sir.
Oh, okay. Yes.
Correct.
And that shaded
Yes,
portion.
Yes, sir. Got it.
And like these points, these are all, if you union all those points, these are all points in this region. Any if you
Got
took
it.
any point,
That is the bounded region. Got
yeah,
it.
this
Sir.
is the bounded region.
Yes,
bounded region.
Yes, yes, got it, sir. Thank you.
What I wanted is the probability that x
is greater than y.
X comma y. This is a joint PDF, right? Jointly distributed. I want the probability that x is greater than y. So this is the region I want. So I just wanted to compute. I have the density with me. Yeah, I have the density with me. I have the area with me. I just have to compute the probability. How I am computing?
Now it's clear, sir.
Yeah,
We are
I am
taking limit
computing
with respect to bounded region. Yes.
Yeah. So probability is actually equal to density times area, right? So that is what we are doing. So dx dy is the area, and this is the probability density. If you multiply density with area, you will get the probability. Okay. So you just have to integrate it. 0, 1, 0, x. This is 4xy dx dy. So sorry, dy dx. So you integrate it. You will get so 0, 1. You bring 4x outside. This will be 0 to x y dy dx. 0 to x y dy. This is y square by 2. You will get x square by 2. So this will be 0, 1, 4x cube by 2 dx. Okay. So if you again, this will be 0, 1, 2x cube dx. This will be 0 x power 4 by 2x power 4 by 4, 1, 0. Okay, we got half only.
Half, yes.
Half only.
Yeah. See, because you will get to know why this is off, because x and y are independent here. We will see one interesting thing.
And there is quite possibility that the probability can be from the other white place also, sir. So it could be half.
See, if this is half, the other part is like 1 minus half. You know this whole region probability is 1.
1.
Yes.
If this is half, that is actually 1 minus half.
True.
Okay. Yeah, and there are some other things will be like probability that x is less than 0.5, comma y is less than 0.5. So which region will this represent? So okay, let me draw it again. So we have this is 1, this is 1, and this is the unit square we have. Now tell me which region is actually representing probability this event, x less than 0.5 and y less than 0.5.
1 by 4.
It's 0.5, 0.5.
0.5 area, sir. Like at the midpoint of this.
Okay, let me
between 0 and 1.
Just tell me whether this is correct or not.
Yes. And yes, this area.
Correct.
This is the region, right?
Yes.
And this point is like 0.5 comma 0.5. Okay. For this region, you just have to integrate from. See, you see, x goes from 0 to half.
0.5.
Okay. So whatever x you take, y actually varying from 0 to 0.5. Right? So whatever x you take, y is actually varying from 0 to 0.5. So 0 to 0.5, and even the y limits are from 0 to 0.5.
Yes.
Correct? And fxy of x comma y dx dy. So we add all the densities multiplied with those areas. We add all those things, all the points. It's just like integrating is nothing but adding all those points, probabilities. We will get the total probability. Okay. This is how some events, even it is non-uniform, or even if it is uniform, this is how we compute the probabilities of some smaller events defined on this joint xy. Okay.
May I request something?
Sir, can I ask a question?
If you have the answer to this, can you just give the answer? I would like to compute later.
Answer. I
How
don't
does
have the answer. I just
okay, fine.
4xy.
From the figure, yeah, from the figure we can easily estimate, sir. From the figure you can easily estimate the total picture will cut into 1/4 kind of thing, the region area.
But the density is really
But
high
the
at
density is different, right?
Yeah.
It's not
Density
uniform.
is different.
Okay, let us compute and see whether here
I think it's for the best. Yeah.
No, here it is independent. Okay, let's see. Let's hope.
Yeah, again it will come same.
0 half, I will bring 4x out.
0.25, I think.
Yeah, we are getting 0.25 only. So this is 0 half 4x, and this will be y square by 2 half 0.
1 by 8.
It should get lesser. You won't get the 0.1. So this is 1 by 8. So
1 by 8.
You will get x by 2. Right? This is 1 by 8. And this 4 times 1 by 8, you will get half dx. This is again x square by 4.
4.
And this is half 0. We are going to get
1 by 16.
1 by 16. So why we are getting
Very
1 by
much
16?
less.
See, just now we discussed the probability that x takes values around 0 are much more lesser than the probability that x takes values around 1. So here the density is higher and the probability will be higher. And if you come slowly towards 0, the density is lower.
Lower.
As the density is lower, the probability that x and y takes values around these intervals are also lower, will be lower. So that is what we just seen. So the density, the probability that x and y takes values between 0.5 to 0 is only 1 by 16. So that means if the probability density function is like 4xy, so probability that x and y takes values more than 0.5 is more than 0.5 is much more higher than less than 0.5. So if you compute the more than 0.5, the region will be this. This region. You just compute the probability that x is greater than 0.5 and y is greater than 0.5. You will get something very much more greater. You might get more than half also. Okay. So the limits will be, now you can see the limits will be from half to 1 and half to 1. Right? X limits are from half to 1. This is half, this is 1, and this is 1. So x limits are from half to 1 and y limits are from half to 1. We take this as an exercise and do it out. So half to 1, 4xy dy dx or dx dy. So you just compute the integral of this, just same like this, just the limit changes. So I hope it should be greater than half. will be greater than half.
Yes.
From these probabilities also you can actually interpret the densities. So that as the densities are higher, the probabilities will be higher in that region. Okay. Okay, that is about joint probability density function and if the two continuous random variables are jointly distributed, that is how we compute the probabilities of some smaller events. And yeah, we will look into this much more detail. And before that, we will just see this sub topics kind of things like how do we compute the marginal density. Marginal density is actually, even in discrete case, marginal PMF is actually the PMF of X.
X.
So if you look the PMF separately, if you look at the PMF of X separately, that is nothing but the marginal PMF. Here also the same thing. So marginal densities actually,
So here it will be
probability
marginal
density.
PDF.
Yeah, marginal PDFs are nothing but the PDFs of individual random variables.
Random
X and Y
variable.
are individual. Whatever the PDF this affects X, random variable X has and random variable Y has, those are the marginal densities. So only the name change, but the same convention. Okay, and this will be, if you wanted to compute the marginal density of X, fx of X will be, you have to integrate it over Y, complete Y. So from minus infinity to infinity, you just have to integrate this xy. So Professor Andrew's statement is also like
dx, sir.
dy.
dy.
These are y limits. You are integrating over y.
Okay.
Okay. So what you want, take it. What you don't want, you sum it. So that is how you can get the marginal densities. So we want the marginal density of X, random variable X. So what you do is, you just sum over whole support of Y. You just sum over whole support of Y. What you will sum over? You will sum over the probability density function. Okay. So same way, if you want to find Y marginal density, you sum over X. You sum over the probabilities of
dx.
Dx. Here it will be dx. So you are integrating the limits. What you are going to write is of X. So you are integrating along X. Okay, you are summing. Integrating means you are just summing all X's, because I don't want X. I want marginal density of Y. What I will do is, I will take the support of X and I will add all fxy of X comma Y dx. Okay, so these are marginal densities. And
take examples.
Example of this will be, let us take activity example only. I didn't create any example. Let us take activity example. That will be
The professor will also talk about some slicing and also what is that concept?
Slicing?
Yes, so like this kind of, when we are talking about marginal probability, right? So for example, for X, we are keeping X constant and we are integrating over Y, right? So through pictorial, he is saying that let us take a slice and then we are trying to
okay.
He was asking us to visualize it, that how the graph will look.
Yeah, I got it. So okay, let me take the example and
Yes, sir, yes,
I will
yes.
try to
Yes,
slice it, do the slicing thing. Okay. If you guys are before laptop, just open this week 6.2 AQ 6.2, and what we do is, we take question number 2, which has some bigger region. Okay, so it says xy is uniform in region D. So one example is, this xy is uniform in some region D, and region D is given as
0, 1,
0, 1,
cross 1, 2,
comma 2,
union 1, 2,
1, 2,
cross 0, 1, union 2, 3, cross 0, 2.
Okay, so this is combination of 3 regions, and
Yes.
collectively we call the region D, and XY is uniform on this region D. That is what it is given, and they are asking the marginal densities of
X and Y.
X and Y. Okay, first and foremost thing is, if you draw the graph, it will be easier for us to
So
visually
every
look.
time we have to draw the graph.
No, not every time you have to draw. If you are
Because
unable to use the formulas and everything, then
no,
graph.
it becomes easy to visualize.
Okay. First and foremost thing is we draw the region of D. So we find the region of D. So there is 0, 1, there is 2, and there is 3. Here it is 1, 2. Okay. So first region is 0, 1 cross 1 comma 2. I said this represents a region. So this represents 0, 1 cross 1 comma 2. So the region is this. This region.
Yes.
And the second region is 1 comma 2 cross 0 comma 1. So this will be the region. So this is the first region, this is the second region, and the third region is 2 comma 3 cross 0 comma 2. Third region will be like this, 2 comma 3 to 0 comma 2. So 2 comma 3, 0 comma 2. So this whole region. So this is the region. So now that we got the region, we have to find the marginal. So it is uniform. So once it is said uniform, you just find the joint probability density function. So how do we find that? We have to compute the area of this region, whole region. What is the area of this particular region?
1.
1. Area of this?
1.
Area of this?
2.
So what is the area of region D?
Last one is 2. So total is I think 4. Then.
4. It's like right. See, the region D area is like union of these areas.
4.
So the total area of
4.
The region D is the total area, which is 4. If the area is 4, the joint PDF will be
1 by 4.
1 by 4.
Yeah, 1 by 4. Okay.
You can take a fresh message.
So the joint PDF will be 1 by 4 x comma y in region D and 0 and 1. Okay. Now what we have to do is you have to find the marginal densities. So how do we find the marginal densities? Is if you have the graph, what I will do is, see this region. So in this 0 to 1, okay, let us find first the marginal density of x. So I just want the marginal density of x. So I just want to find this. So what you have to do is, you know the support of y. So sometimes y takes 1 to 2, sometimes y takes 0 to 1, sometimes y is taking, whatever the y you see, it takes between 0 to 2. Correct? So I just have to integrate it with 0 to 1, 0 to 2. But if I see this xy, x comma y, dy, so ultimately I have to find this value. But you see in this particular region, the y values are from 1 to 2.
Yes.
And in this particular region, the y values are from 0 to 1.
Yes.
Okay. And in this particular region, the y values are from
0 to 2.
0 to 2. So depending upon the interval of x, the y values are varying actually. Okay.
Yes.
So what we have to do is we split them as intervals. Okay. So in this, when x is in between 0 to 1 interval, so different cases, that's it. So what we do is
Three different cases.
3 different cases. So let me write it here. So 3 different cases are when x is in between 0 and 1. So equality or not equality doesn't matter. Okay, in continuous case, at one point you include one point or remove one point, it doesn't matter. So from 1 to 2 you have another case, from 2 to 3 you have another case. So in this region, the support of y is from 1 to 2, fxy, x comma y, dy. And in this region, the support of y is
0 to
from
1.
0 to 1. So you just see the graph of it.
So here we are taking the values of y as support.
Yeah, y as support.
We
So
want
you
to take the effects.
you take from minus infinity to plus infinity, but from minus infinity to 0 and from 1 to infinite, the value of fxy of x comma y is 0.
0.
So anyway, it will go off and you will only integrate along support. So
Okay.
0 to 1 fxy x comma y dy. And the final one is from 0 to 2 fxy x comma y dy. So this will be the marginal density of x.
Okay.
Okay. So if you find the values, what will you get? This is 1 by 4 actually. So this is 1 by 4 times 1. 1 by 4 times 1. You will get this value as 1 by 4. This value as 1 by 4. This value as 1 by 2. Just compute it. Just simple. So it is 1 by 4. Integral 1 to 2 1 by 4 dy will be y by 4. Limits from 2 and 1. So it is 2 by 4 minus 1 by 4, which will be 1 by 4. Okay, I just said it with mouth. You just compute it. You'll get 1 by 4, 1 by 4, half. So now you see from 0 to 1, it is 1 by 4. From 1 to 2, it is 1 by 4. So you can actually combine those two and write it simply like 1 by 4 when x is in between 0 to 2 and half when x is in between 2 to 3. Okay.
Sir, can you please explain how did you get that fxy xy 1 by 4 in the region D?
It is like it is given uniform, right? In the question itself, x and y joint distribution is uniform on D. So when it is uniform on D, we just discussed this uniform case. When it is uniform, when it is uniformly distributed, they have joint density as 1 by mod D, where mod D is the total area of the region D. In the region xy belongs to that region D, and 0 otherwise. So this is what we used. We just found the mod D here. So mod D is nothing but the total area of D. Total area of D is 4. So as this total area is 4, this is 1 by 4 is nothing but the 1 by mod D. So mod D is the area. So the area is 4. So it will be 1 by 4. 1 by 4 in this region and 0 in otherwise. So this is how we find the joint PDF of an uniformly distributed.
So sir, in last part it's 1 by 2 from 0 to 2.
Okay, last part is like we are integrating 0 to 2, 1 by 4 dy. So this will be y by 4 from 2 to 0. So it will be 2 by 4 minus 0. It will be half. If we are integrating it from 0 to 2. Just the integral computations. Okay.
I have a question on the ranges that you have picked here. The inequalities for 0 to 1, it's is x greater than or equal to 0 and x less than 1. But when it came to 3, it is x less than or equal to 3. Is it because it is a closure of the range?
Closure of the range. I just said, right? Even if you keep equality sign, or if you remove the, if you add 1 point or remove 1 point, it doesn't affect much in continuous cases.
Okay.
Because probability at that particular point will be 0.
Okay.
Okay. Yeah. So yeah, this is how, this is the marginal density of x. If I wanted to find the marginal density of y, I wanted to find this. Even this, you see here, from 0 to 1, I have x varying from 1 to 3. Right? From 0 to 1, so x varies from, so if I take this, this is the part. So whatever the value from 0 to 1 I take, x will take from 1 to 3. Whenever y is from 1 to 2, x takes from either 0 to 1 or from 2 to 3.
Okay.
Correct? In this region, you see it as a two different cases.
Areas.
Two different cases. So from 0 to 1, y when it is from 0 to 1, the below case, this case. So y takes from 1 to 3. Values of y takes from 1 to 3. So the support of x is actually from 1 to 3.
You mean x takes values from 1 to 3, right? You mean
x takes. Sorry, x takes values from 1 to 3.
X takes values.
When y takes values from 1 to 2, x takes values from 0 to 1 or 2 to 3. So when y is taking value 1.5, x cannot take value in between 1 and 2. Right? So there is no point. This region is not covered in our density function.
Can you explain one more time, please, sir?
Okay. So what I wanted to tell is how we break down, when we are computing marginal density of x, we break down this x interval to 3 subintervals, 0 to 1, 1 to 2, 2 to 3, because for each interval, the support of y is different. So in this particular interval 0 to 1, the support of y is actually 1 to 2. When 1 comma 2, in this region 1 comma 2, in this interval 1 comma 2, y support is 0 1, not 1 2. So y support changes when x interval changes. Similarly, when you see in y case also, when your y takes values from 0 to 1 in this interval, your x support will be from 1 to 3.
Yes.
And when y takes from 1 to 2, your x support is from 0 to 1 union 2 to 3. Okay. From here and here. So the same thing we do here also. What we do is, गाना बजा रहे हो? Is it so?
I also felt.
Okay. Okay, fine. Okay. So Fy of y, if I wanted to compute, I just split the region of y, split the support of y to 0 to 1 and 1 to 2. So in 0 to y, my x support is from 1 to, 1 to 3. 1 to 3 fxy x comma y dx. So here when y is in the interval 1 to 2, my x is from 0 to 1.
0 to 1. Plus.
And 2 to 3.
2 to 3. Okay.
Okay. So from here you just have to compute. You just replace fxy x comma y value as 1 by 4. Then you will get 1 by 4 dx. And 0 1 by 4 dx plus 2 3 1 by 4 dx. So if I compute this value, you just compute this value, you will get x by 4. So 3 by 4 minus 1 by 4, you will get 2 by 4 equals to 1 by 2. So 1 by 2 in the interval this. And even here also, if you compute it, you will get this as 1 by 4 and this also as 1 by 4. 1 by 4 plus 1 by 4, you will get 1 by 2. So even if it is in the region interval 0 to 1 or in the interval 1 to 2, the marginal density is half.
So we have to calculate region-wise marginals.
We have to
calculate marginal density region-wise in different regions.
Region-wise, and I will now show you the interesting part. And this you can combine 0 y 0 2 and 0 otherwise. So you see, this is the marginal of y. Now let's just go back.
So how it's 0 to 2 now?
See, even if it is from 0 to 1, it is half. 1 to 2, it is half.
Okay.
You can actually just combine and say, in the interval
okay.
0
Instead
to 2,
of
it takes half. Yeah.
Okay.
Now just come back. So we have densities with us, right? So you see here, whatever the area you see in 0 to 1 and whatever the area you see in 1 to 2, they are equal. And half of the area lies in the interval 0 to 1 and half area lies in the interval 1 to 2. Okay. Out of the
You're talking about y support?
Huh?
Y support?
Y?
Y
I'm
support
talking
you're
about the y support. So we just got Fy marginal density as half in the interval 0 to 2 and 0 otherwise. This is what we got, right? So you just see y separately. You don't bother about x. So what I will do is, so now that I am not bothering about x, I can actually move this particular rectangle here or here or here. It doesn't matter. I am not worrying about x now. Okay. I am just worrying about y. So I just wanted to remove this x axis completely. Okay, if I remove that x axis and if I draw it like this, so this is 0 1 2. So you say this is y, this is the y I drew, and in this 0 1 I have two boxes. Okay, and this 1 to 2 I have two more boxes. Correct. I have total of 4 areas. Even if you
each having 1 by 4.
Yeah, these are 4 areas. Okay, you just treat it as these are 4
And this
areas.
is coming under even distribution, no, sir?
Yeah, even
uniform.
Yeah.
Uniform.
Now this becomes an uniform distribution with area. With area, you see this is 2 and this is also 2, right?
Yes.
This is half.
Which is half?
Yes, we are taking the height, sir.
Total is 4. That is 2. This is 2. Is this correct? Half is correct, right? Not 1 by 4.
Right,
No?
sir.
It is half. Huh?
The first figure is for the basis only, sir. The probabilities will be rising along the z-axis.
Yeah. Probabilities will be rising along the z-axis is okay.
So here we are taking the z-axis as a height for y, marginal of y. So it will be half.
Wait, that only.
The height will be the z-axis in this figure, na sir?
Height will be the z-axis. No, I'm not talking about that. I am just confusing now. Just give me 1 minute. Okay. We need to get half. Density is half in this interval. Oh my god. Anyone? I just said anyone have this intuitions?
So if it's 1 by 4, when we multiply it with the length, it will be 1 by 2.
Sir, y is along 0 to 2
never
and
mind.
the marginal is going to be 1/2. So the area you are calculating, the area should be 1.
Area should be 1.
1.
Area
So
should be 1, is it?
Yes. So the height will be half. Height of this figure.
Height of this figure is half. I'm getting that.
Right.
So half
And the
gives.
axis will be z-axis.
Axis will be z-axis.
Yes. Z-axis of the first figure.
Okay, but how come this particular area came 1?
What area, sir? Actually, you can't draw the four rectangles like this in this figure, na sir.
Okay, let us see with 3-dimensional
These
only.
are x-y axis.
Okay, this is x and this is y.
This is y. And our area lies along the xy plane.
Our area lies along the xy. Okay. Okay. This is not this area. We have this. Yeah, this and something like this.
Right.
And something like this. Correct?
Right.
So this. We have this. We have.
And the probabilities are along the z-axis.
So this is 1 by 4. This height will be 1 by 4. This height will be 1 by 4. Correct?
Right.
So the height is like
Can
1
you
by.
come in, please? I just got confused here.
He's showing a 3D picture.
This thing we can confuse because I am drawing 3D in 2D paper. So definitely, even see, you give me 5 minutes, even now I will forget what line I drew. Even I will forget. I'm just making what I say. Let me understand first, then I will explain you.
Okay.
I'm just
That's
trying.
always better.
Yeah, this is 1 by 4. Okay.
Right.
Okay, this is okay. But now I want the individual.
So the probabilities along the y-axis will stack on each other, na sir?
Will stack on each other.
And then the height will be 1 by 2.
Right. This. Okay, this height is only 1 by 4, right? If
Right.
we stack it up, you will get half.
That's
Half.
Correct. Correct. Okay, so this is actually half. Correct? Half and half. This will become
1/4, 1/4, sir. This is 1/4, this is 1/4. Total will be 1/2.
Total will be 1/2. No, this is not height. This is half part of it, and this is half part of it, right? This is half and this is half. This will come as height. I am looking at this thing and this 1 by 4, 1 by 4. What is this? Zero. See, this will stack up, this will stack up, it will come to half. Okay. So now your stacking will be like this. Yes. No, what is this? This is 0 to 2.
0 to.
What is this?
This is a small.
This is nothing actually. Okay, fine. Why am I? See, in my individual continuous case, so if we are talking about a single variable continuous case, we have only two axes, right?
Right.
Why am I bringing the third one? Okay. Correct. Whatever you said is correct. Okay. So I am okay now. Let me explain you guys. So this is wrong. So see, this is the marginal PDF. And this will actually be equal to the individual probability density function of y. So if you look at the individual probability density of y, you see here, out of 4 parts, you have 2 parts in the interval 0 to 1, and you have 2 parts in the interval 0 to 1 to 2, right? 2 parts here, 2 parts there. So each part has probability density function as 1 by 4. So if each part has 1 by 4, in 0 to 1 you have 2 parts, and 1 to 2 also you have only 2 parts. Okay. So for one part you have joint PDF as 1 by 4. For 2 parts, how much it should be? So if it is one part, you have 1 by 4.
1 by 2.
1 by 4 plus 1 by 4, it is 1 by 2. Even in the interval 1 to 2, you see there are 2 parts. 2 regions actually. 2 regions. If you add those regions, you will get 1 by 2. Whereas if you see the x interval, you see out of the 4 regions, you have 1 part in the interval 0 to 1, 1 part in the interval 1 to 2, and 2 parts in the interval 2 to 3. So that is why if you compute the marginal PDF of x, you have 1 by 4 in the interval 0 to 1 and 1 by 4 in the interval 1 to 2, but half in the interval 0 2 to 3.
On adding it is becoming 1.
Hmm?
On adding it is becoming 1. It is satisfying.
Yeah, it will satisfy. See, you have only one part in the interval 0 to 1. So one part means 1 by 4. PDF is 1 by 4.
Correct.
Okay. So you have 2 parts in the interval 2 to 3. So that is why you got 1 by 4 plus 1 by 4 as half. Here. Half in the interval 0, 2 to 3, 1 by 4 in the interval 0 to 2. Okay. See, and adding all to this, if you don't know anything of this, you know how to compute the marginal densities, it's fine. It's nothing else. I'm just trying to give you intuition, and in between I forget
Good
something.
insight, sir. This is
Yeah,
good insight.
I forget something. I made you confused. You confused. I confused. Lot of things has happened, but ultimately I just wanted to give you this one statement is like marginal PDFs are not new things. Marginal PDFs are nothing but the individual PDFs of X and individual PDF of Y.
Yes.
Okay. So yeah, that is about.
Yeah, that's clear.
Joint still is something you can compute from product of conditional into marginal.
That is that everything is same. See,
Okay.
whatever you do in discrete, in continuous is also same. Only
Okay.
I think we are inching towards that concept while studying conditional, sir. We are going to use that.
So that is about this margin.
Sir, can I ask a question?
Yeah,
Like
yeah.
now that we have found the marginal PDFs, which we are saying as the individual PDFs, can we say something about the distribution followed by the random variables X and Y?
Yeah. Individually. So these are the distribution. So if you see here itself, Y takes values from 0 to 2 uniformly. Okay, that is what it tells you. So if it is taking values from 0 to 2 uniformly, the density function will be 1. Okay.
The height will be 2.
And sir, can you please also say about X?
For X also it's like from 0 to 1, 0 to 2, 3. From 0 to 2, the height will be only 1 by 4. And from 2 to 3, the height will be half. So this is 1 by 4. That means it tells it's not uniform. So it says you that in the interval 0, the probability density is different here. So PDF is not uniform. See, you see this PDF. See, this is something like uniform PDF, somewhat like uniform PDF. So you have same density for all the values in the interval 0 to 2. Right? This is something like uniform PDF, right? But here, whatever X you got, this is not uniform. In some interval it is 1 by 4, in some interval it is half. So the density value changes when X changes. But here the density is same for all Y. So from 0 to 2, the density is same. So if I draw the density graph, it will be like this. For Y, this is for X, this is for Y. So the density graph will be half from 0 to 2.
Yet, when X and Y are combined, they follow uniform distribution, despite X not following a uniform distribution.
Yeah. So X and Y combined, they are following uniform. Y separately following uniform, but X is not following uniform.
Is this some kind of a conclusion that we can draw? One of them have to be uniform, or this is just a special case, or just one of the cases?
No. This happened to be a special case.
Okay, got you. Thank you.
Okay.
So can we go with independence?
Let's move to independence. See, even independence is same thing. So X and Y, we say X and Y are independent if your joint is product of marginals. So few examples are like if X and Y is uniform in this region, square region. So if it is uniform, there are two cases. You can compute the marginals of this separately, and you just product the marginals, you will get the joint. Or else you see, if I vary X and Y from 0 to 2,
Hello, not able to hear you.
We lost his voice.
Yeah.
Hello?
Yep.
Yes, sir.
This one thing doesn't change, I guess. Every time after 2 hours, I will get automatically logged out. Especially for stats too. Even in the last time also this happened. I complained many times. Okay, let me get co-host access meanwhile. I just message them. They'll just give me the access. Okay, the independent case is a similar case which we studied in discrete. I think it's like joint is product of marginals. Okay.
Your screen is not visible.
No. Just wait.
Okay.
Let me get the co-host access. And okay, you can take some 2 minutes break meanwhile. What else have you guys gone through week 7? Have you just opened week 7?
No way, we just closed week 5 yesterday.
No.
Okay.
Sir, can I ask one question? In fact, it's a request. Like during one of the lectures, sir had talked about a particular problem where there are two variables, random variables, and the direct, the joint distribution is not given, but it's given through relation in terms of y equal to some x plus z, but x and z are two random variables. So I would really appreciate, sir, if some of those problems, I mean, I haven't gone through the activities, but are there any problems like those? Or if you can kindly take up one of those problems at the end of
Okay, in
whenever it's
week
completed.
6, I think we don't have that kind of problems. Maybe
Because
we should just
what if the joint probabilities are not given, like, and a relation is given, and how do you exactly find that out? I could do that problem which sir has given, but I'm pretty much sure if something else comes, I won't be in a position to do it.
Okay. So in that case, we just have to go back to week 5 and discuss those things. I don't think week 6 has those things. Okay, we will just go back to. Hey.
No problem, sir. Like you can finish whatever it's in the agenda first.
Okay. Just give me 1 second. Okay. Hello? Can you make me co-host? I don't know why I logged out from stats 2 session. Stats 2. Yeah, hello. Hello.
Yes, sir. Yes, sir.
Okay, we will see. And what else? Anything other than subject? Had dinner?
After class.
Yeah, after class. Because if we have dinner, we'll feel sleepy. That's why.
Okay.
Sir,
Hmm.
at the beginning of the session today, you mentioned something about this course becoming 4 years. Is there any possibility? We are also hearing from many other student groups that this course is about to become 4 years.
It's not confirmed yet. If it is confirmed, then you might see some advanced statistics.
Okay, now your screen is visible, sir. We can.
Yeah. Okay. Okay. See here. Let's come back. Let's discuss the independence thing. So if you see here, we just said xy jointly distributed in the region 0, 1 cross 0, 1 uniformly. So when I said that, if you see the graph, this is the region, and if my x varies, if you see, even it is at 0 or from 0 it starts and it varies till 1, my y doesn't vary. My y is not dependent on this. My y, whatever the x takes, my y can take from 0 to 1, independent of x. So from the region itself you can find, or else use this definition. I'll just show you why this is independent. So this is actually independent. This is independent because this satisfies this condition. So you know, when we said uniform 0, 1, 0, 1, so the area is actually 1. So the density function of this will be 1 in this region and 0 otherwise. So the density function is this. From this density function we know how to compute the marginals. So the marginal of x will be integral, you integrate over y, support of y is from 0, 1, 1 dy. So here we get y 1, 0. We are going to get 1 when x is in between 0, 1 and 0 otherwise. So here also the marginal is same as joint. Even if you compute fy of y, you will get 1. So what we got is fxy of x comma y is 1, which is nothing but the product of marginals, which is 1 times 1. So 1 times 1 is 1. So that is why this will be independent. And what about this? So xy uniform in the region 0, 1 cross 0, 1. Am I audible? Why everyone is silent?
Yes, sir.
Yes, sir.
So 0, 1 cross 0, 1 union 1 comma 2 cross 1 comma 2. So the region will be somewhat like this. Correct? So 0, 1, 2, 1, 2. So now you see. So this is the region. These two, combining these two regions is the combined region. And we said uniform. So the area of this total region will be 2. Therefore fxy of x comma y will be half in the region T, 0 otherwise. Now if I compute marginals, if I have to compute the marginals, so just try to compute the marginals now. Now you tell me how to compute the marginals. So let me take one more page. So we have this region. Let me check how much you understood today. So now you guys should tell me how to compute the marginal. Now we have this region, and also we have the joint distribution, joint density function as half in this interval, in this region, 0 otherwise. Now I want fx of x. Hmm.
1/4 in 0, 1/4 in 1/2.
It's half from 0 to 2. Otherwise, it is 0.
Half from 0 to 2. Otherwise, it is 0. Okay. Okay. Yeah, I think that is correct. But I just wanted to go from step by step. So what I will do is I will split the interval. So x I will split it as from 0, x taking from x in the interval 0 to 1 and 1 to 2. So in the interval 0 to 1, my support of y is from 0 to 1. So 0 to 1 half dy. Similarly 0 to 1 half, this is from 1 to 2 half dy. And we have this as, if I integrate, this will be y by 2. And we'll get 1 by 2 minus 0, which will be half. Half in the interval 0 to 1. And similarly, this will also be half in the interval 1 to 2. So you can actually combine these two. You will get half in the interval 0 to 2 and 0 otherwise. So similarly, if you find the marginals of y, you will get half in the interval 0 to 2. Correct? Correct?
Yes.
Also, whatever I said, look at this as there are two parts. Out of the two parts, one part is in the interval 0 to 1, another part is in 1 to 2.
Sir?
Huh?
What is the marginal of Fy, sir?
Fy is also same.
1 by 2?
1 by 2 in the
So,
interval.
but if I multiply, then it will become 1 by 4, no?
That will become 1 by 4. That is what, right? So I have fxy of x comma y as half. But fx of x times fy of y, I will have half times half. It will be 1 by 4, which are not equal.
Okay.
Okay.
So this is not independent.
So therefore, I say this is not independent. So from the graph also, you see, as the value of x varies, so in the interval 0 to 1, y takes in the interval 0 to 1. But when I change the interval of x, my y interval also changes. So depending upon the x value, my y value is changing. So there is some dependency between x and y. So therefore, it is not independent.
Can you repeat that part, please? Can you repeat that part? Why it is dependent or not independent? Let's say
it's not independent because when I change x, this works only for uniform. Okay.
Where are you pointing at? I can't see that.
Here.
Okay.
So here, when x is from 0 to 1, my y values will take from 0 to 1.
Correct.
Right? And when I change my x values from 1 to 2, automatically my y values also will change and it will start taking from values 1 to 2.
Okay, yeah.
By changing my x values from 0 to 1 to 1 to 2, my y values also automatically changes. It's actually dependent on x values. Y values are actually dependent on x values here. So there is some dependency between x and y. So
that would be the case even if I actually move the probability, let me put it as the triangle, rectangle, the square that is on the right top, if I move it to 2 to 3 instead of 1 to 2 on y, that still would be the case, isn't it?
2 to like this, is it?
Yeah, if I move it there, it still would be the case, correct?
It's the same case. See, if I change x, if my y value is changing, my y support is changing. If I change the support of x, if my y support is changing, then that implies that there is some dependency between x and y.
So the support should not change when the range of one margin is changing. Is that the way to interpret it?
Yeah. In uniform, see here, in this case, you see, along 0 to 1, whatever the value x takes is independent of what y can take. Even the value x taking 0, y can take from 0 to 1. Even it is 0.5, y can take from 0 to 1. Even it is 0.9, y can take from 0 to 1. So whatever, if I change the x value, the support of y doesn't change. Support of y is same for all different x values. So from there you can see some independency. Y is independent of x value. So whatever y takes is independent of x. From the graph perspective, okay, it's just like shortcuts or something like that. You just drew the graph and you don't want to compute marginal densities. By looking at the graph intuitively, if you change the values of x, if your support of y is changing when I change the values of x, then that means depending upon x value, my support is changing. That means y is actually dependent on x. So when one is dependent on other, then we say both are not independent.
Okay.
Sir,
yeah.
So here we are comparing probability densities, right? We are not comparing probabilities. We are comparing densities.
Densities only.
Like product of their individual densities should be equal to the product of their joint density. Sorry, their joint density, right?
Joint density, correct.
So
these are
one observation is there, like in all the diagrams so far, whatever we have drawn, the range of x is in continuation, right? What I mean by continuation, say for example 0 to 1, and then in the next block it is 1 to 2 and then 2 to 3, right? So is it by design or by coincidence? Like is it a needed condition? It may be that two blocks are different, right? That is quite possible, right?
Possible.
Okay.
Yeah, that is we defined. Like, see, one I can have here and other I can have here, and other I can have somewhere.
Okay.
It no need to be continuous, but whatever the intervals are there, they are continuous.
Correct.
So union of intervals.
That we have to take care.
Yeah, that you have to take care.
Do these cases always mean that x and y are dependent?
In these cases like this, if my x is changing, if my support of y changes, then they are not independent. By looking at the graph itself, we can say. Okay. Or you just have to compute this marginal densities and see the product of it, and if it is equal to point density, then they are not independent. If it is not equal, they are not independent.
Okay.
Okay. Yeah. And final thing is like conditional density. So conditional densities, see here you see, now we are fixing some condition, and depending upon that condition, we just find the density of other random variable. So for some a, such that my marginal density of x at that value, at that a, is greater than 0. So this is some required condition because we are dividing it by, so in conditional density we are going to divide it in the denominator. So this should be greater than 0. It should not be equal to 0. Okay. And the same formula we have, fy given x is equals to a of y, which is nothing but the conditional distribution of y given x is equals to a is nothing but equal to the joint divided by marginal. So conditional is equal to joint divided by marginal, and in this joint and marginal we fix one particular condition. So we just fix that x is taking value a. Okay, this is the condition. So whatever the condition is given, depending upon the condition, what is the conditional density of y? So if x is equals to a, if x is equals to a is given, or if it is conditioned x is equals to a, what is the density of y? So that particular conditional density is nothing but equal to the joint divided by marginal. So joint we know fxy of x comma y, and x is taking value a, so it will be a comma y divided by fx of x, which is again x takes value a, so a. So this is conditional density, and few examples are like same thing. I just wanted to go back to activity questions now. Anyone who did week 6 and had doubt in week 6 AQ, 6.4. You can just post your doubt here. Or else I will just simply take the first question. Okay, let me take the first question. An example from the activity itself. So we have given you the joint density as 6x square y. So in the interval, x interval is 0 to 1 and y
which
interval
AQ is this?
AQ 6.4 and 0 otherwise. Okay. So this is the joint density given to you. And once the joint density is given to you, it is asked that you just find the probability that y is greater than 0.5 given x is equals to 0.5. So this is nothing but we need to find integral 0 to 5. See, if it is discrete case, what will you do? If it is discrete case and we said y is greater than 0.5, what we will do? We will be summing up from 0.5 to the above value, which is infinity. Correct? fxy of 0.5 comma. Right? We will sum it, right? So what is the probability that y is greater than 0.5? What is this? Let me still go back. Okay, my x is taking values 0, 1, 2.
The limits are y from 0.5 to 1. Is that what it means?
Correct. So x is, let us see the discrete case and we will just combine it. So x takes value 0, 1, 2. What is the probability that with probability is 1 by 2, 1 by 4, 1 by 4. Okay. What is the probability that x takes value greater than 0? What is this means?
1 by 2.
No, 1 by 2. But I just want the intermediate step.
Yeah. So probability of x equal to 1 plus probability of x equal
probability
to 2.
of x is equals to 1.
That is nothing,
but we are actually summing.
Yes.
Right?
Yes.
Which is greater than 0. We are summing up all. So x belongs to tx and x greater than 0.
Probability of x equal to xi. Yes.
So x belongs to the range and also the x should be greater than 0 is the condition. So we will sum all those things. So here also the same thing we do. But here I just said in continuous case what we do is this sum will be replaced with integral. So if I want the probability of y greater than 0.5, this will be something like 0.5 to 1. Okay. fxy of xy this will be the probability. Okay. Yeah. Now we'll come here. Now we have to find the probability that y greater than 0.5 given x is equals to 0.5. So this is nothing but probability that y greater than 0.5 comma x is equals to 0.5 divided by we don't say probability that x, these are continuous cases, right? So what we say is fx of
0.5 in bracket 0.5.
Where in bracket 0.5?
Yeah, it is correct, sir.
Yeah. So the above one is nothing but 0.5 to 1. So we have only till 1. So you can keep it infinity and also, but 1 to infinity it is 0. So it will come down to 0.5 to 1. fxy of, this is the joint distribution. fxy of 0.5 comma y dy. Correct? Is this correct? So this is nothing but the joint distribution. So you see the interval also. So this is 0 to 1 and 0 to 1. Y is greater than 0.5 and x is equals to 0.5. So x is equals to 0.5 is this, and y is greater than 0.5 is this to this line. We are looking at this line. Okay, from y greater than 0.5 and x is equals to 0.5. So x is equals to 0.5 is this, the whole line, 0.5 line, and in that line we need y greater than 0.5. So this line we are going to integrate. So you just, this line is nothing but the union of sum of all the points on this line. That is what we are doing. From 0.5 to 1, we are actually adding all fxy's of 0.5 comma y, where y is from 0.5 to 1. So this will give you this line, complete line, and the numerator is equal to that, this line. Okay. So we are looking at this line where y is actually going from 0.5 to 1 and x is 0.5. So this, on this line there are infinite number of points, right? There is 0.5 comma 0.5, 0.5 comma 0.5, 1, 1, 1, 1, 1, like this. There are infinite number of points. So in order to sum up all those points, we simply replace it with integral 0 to 0.5 to 1 fxy of 0.5 comma y. So where y takes all the values in between 0.5 to 1. So this is what. So the numerator is simply this fxy 0.5 comma 0.5 plus fxy 0.5 comma whatever the next real number which is after 0.5. Like this, it will sum over all the values and it is nothing but integral of 0.5 to 1. So you have to do this. So we know fxy is given as fxy of x comma y is given as 6x square y. So what is fxy of 0.5 comma y? You just replace 0.5 in place of x. 0.5, 1. So 6 times 0.5 square times y dy. So this is half square 1 by 4, 6 by 4, 3 by 2. This will be 3 by 2. So this integration you can compute, right? So 0.5, 1. So 3y by 2 dy. So numerator is this. What will be the denominator? How to compute fx of 0.5?
From 0 to 0.5, sir?
Integration from 0 to 0.5.
1 6.5y.
You just find the marginal first, fx of x.
Right.
How do you find the marginal?
Integrate over y.
Integrate over y. So 0, 1, 6x square y dy. So what will get? 0, 1, 3x square y square. So this is 3x square y square 1 to 0. So this will give me 3x square. Okay. Fx of x is 3x square. So what will be fx of 0.5?
So
3 times 0.5 whole square. Correct?
3 by 4.
Yeah, 3 by 4. It will be 3 by 4. So you just compute this. This will be something like 3y square by 4, 1 half, and divided by 3 by 4. And if you substitute 1 and half, this will be 3 by 4 of 1 minus half, 1 minus 1 by 4, divided by 3 by 4. This will get cancelled and we will get 3 by 4. 3 by 4 as the answer. Just check once you do this activity, you just come back to the session and check whether the answer is correct or not. And I hope this is correct. I haven't made any mistakes.
So you simply are finding the value of the function, and that is my density, right?
That is the density. Yeah.
Yes. So like when I integrated fx, I found out the marginals of x, right? So I got 3x squared, correct? So now while I am putting x equal to 0.5, it is nothing but the value of the function.
Yeah, value of the function.
Correct.
That is the probability density
at that point.
At around x is equals to 0.5. Okay. So this is how we compute conditional distribution, conditional densities also. For conditional density, you can find it using joint and marginals. Okay. And what else we have? We have something like, okay, let me take question number 3 in this conditional, so that we will get some good ideas. So the question number 3 says xy is uniform in the region D in the same activity. Question number 3 says there is some joint distribution xy which is uniform in some region D, and where D is interesting. Region D is actually 3x greater than y and x is in between 0 to 1 and y is greater than 0. Okay, now we will use all the concepts today we learned and we'll try to answer whatever the question is given. Okay, first and foremost thing is draw the region. So tell me the region. Which region will represent the D? So what is the region on xy plane? This is x, this is y. I want, okay, intervals are also given. It is from 0 to 1 and y is greater than 0. So now I want the region of D. Okay, tell me, will it be square, rectangle, triangle, pentagon, or some other amoeba shape?
Triangle.
Okay, triangle is correct.
Should be greater than y by 3.
So how do we get this region first of all?
I think it's rectangle.
How do we get these regions like x greater than y or y greater than x plus 1?
The last two conditions make it a rectangle which is infinite in y.
First of all, we take equality, sir.
That will be the first part.
X is greater than y by 3.
X is greater than y by 3. Okay. So
Sir,
I want.
Sir, just to answer your question, what did you say? How to identify? So the first step, what we do, this is generally we take equality. So I will treat 3x equal to y.
Correct.
Yes. X will be y by 3. And then I will find out.
Yeah. Take equality. Correct. Whatever you said, the first step is correct. Y is equal to 3x I will get. So you take the equality and that will form a straight line equation. So y is equal to 3x is a straight line. And what is this? How that will look like?
Slope of 3.
With slope 3 and passing through origin.
Yeah.
Correct. Okay, I'm doing. Okay. Like this. Right, this line is y is equals to 3, let's suppose. Slope is 3 with passing through origin, and this is 1. Okay. Now once you take the equality, you have two regions now. the upper region of the line and the lower region of the line. Okay. These two regions, one region represents, this particular region represents y greater than 3x, this above region. And this below region represents y less than 3x. Okay. You can check by taking random points. Every point above this line will satisfy this condition y greater than 3x, and every point below this line satisfies y less than 3x, and every point on that particular line satisfies y is equal to 3x.
So this is true for all inequalities.
For almost all the linear inequalities.
Yes.
And I think in our stats too, we don't have other inequalities, right? Do we have higher degree inequalities? Something like y less than x square. See, even if you have those, I will just give you some intuition. See, everything can be plotted on curve on xy plane. So let's say y is equal to x square. So how will y is equal to x square look like?
Parabola.
Parabola passing through origin, correct? And even this parabola divides this xy plane into two regions. One is inside region and one is outside region. This is y is equal to x square, and whatever the point outside this y is equal to x square, you take any point, you randomly take any point, y will be less than x square, and you take any point inside this, y will be greater than x square. So each region, this region, and this line, this curve. So on this curve points will satisfy y is equal to x square. Inside this will satisfy this condition y greater than x square, and outside we have y less than x square. So this is how the inequality regions can be found out. And yeah, here it is given 3x is greater than y, along with condition that 0 is x is in between 0 to 1 and y is greater than 0. So now our region will be x should be in between 0 to 1 only, and also 3x should be greater than y. So this particular region, intersection of all these things. So 0 to 1 is this region. So this particular region, and y is greater than 0 and y is less than 3x is this region. So intersection region will be this. So this represents the region D. Okay, once you got D, our next thing is to find. So what is the first thing we did today? Silence. What is the first thing
we identified the region? We identified the region and then we found the density function.
Density function, correct.
Yes.
So now what will be the density function here? So our region is given to us. This is the region. This is the region. This is the region given to us. And it is said that it is uniform 0 to 1, and it is, what is this point?
3, right?
1 comma
3.
Y is equal to 3x. So
1 comma 3.
Correct. Correct. So what is the area of this region D?
So half into 1.
1.5.
Half into 1 into 3.
Which is 1.5, which is 3 by 2. Let's say 3 by 2. So now what will be the joint probability density function? 1 by 3 by 2, which will be 2 by 3. In this region where x comma y belongs to region D, and 0
otherwise.
0 otherwise. This is 2 by 3, 0 otherwise. So now we have a joint probability density function. Can we compute marginals?
Yes.
Yes. So what will be the marginals now? How do we compute the marginals?
And x integrating over y.
Integrating over y.
Yes.
So from where to where?
X value.
What is the support of y here?
Yeah, 0 to 3.
0 to 3. Okay, 0 to 3. Any other?
It varies along with x values.
It varies along with x. Correct. The support varies along with x. So if I wanted to compute here, so what is the range of y, or what is the support of y? Here, let's say x. What is the support of y?
3x.
Yeah, 0 to 3x. Correct. So at point x, the support of y will be 0 to 3x. So we are computing the marginal density of x. So at point x, the support of y will be from 0 to 3x. Okay, 0 to 3x, 2 by 3,
2 by 3.
y. So this will be 2y by 3, 3x, 0. And this is 2x. 2x. Marginal is 2x. And what is marginal of y? So now the same thing, here you took at random x, I take random y. So random y, from where it is going? So what is the support of x?
Y.
This is y by 3.
Y.
Y by 3 to 1. Correct? This is the slice.
Y by 3 to?
Y by 3 to 1, right? So it goes till 1. So this is the rectangle. So you see randomly slice it here. So this is y. So what is the support of x? So here it is this, here it is this, here it is this, right? The left side, the left point is changing, the right point is constant 1. And the left point is changing according to y. And that particular left point, how it is changing? If it is y, this point is y by 3. If it is something like 0.1, it is 0.1 by 3, like this. If it is y, it is y by 3. So the left point changes, but the right point, the support in the support of x, the right point is constant. So it will go to 1. But the starting point is different. So sometimes it starts at 0.1 if my y value is 0.1. Sorry, 0.1 by 3. If my y value is 0.2, it will be starting from 0.2 by 3. If it is something like 0.9 or something, 0.9 or something, it will start from 0.9 by 3. If it is y, it will start from y by 3. Therefore, the interval is like y by 3 to 1 and 2 by 3 dx. So this will be 2x by 3, 1 y by 3, 2 by 3 minus
Y by 9.
y by 2y by 9. Okay. So 2 by
6 minus 2y by 9.
Fine.
Okay, you can do this. 1 minus
y by
3.
Okay. Okay. So this is the marginal of x. This is the marginal of y in the intervals. This is 0 to x to 1. And what is this? 0 to y to 3. Support of y is from 0 to 3. Okay. So now that we got a marginal, now let's come to the question. The question says y given x is equals to a follows something. Y given x is equals to a. So that means we need to find fy of x is equals to a of y. So this is fxy a comma y divided by fxy fx of a. So now now this is the condition we have. Now tell me, what is this follow? What is this? So x is equals to a is given to you. Okay. So that means this particular thing, this is given to you. X is equals to a. We are asking you the conditional density of y. So if it is x is equals to a given to you, y varies from 0 to 3a. Correct. So 0 to 3a, and what is the probability that y takes 0.1, and what is the probability that y takes 0.2, or what is the probability that y takes very nearer to 3a? So is the density varying or is it the same? So my question is, what is fxy of a comma 0.1, and what is fxy of a comma 0.2, and what is fxy of a comma y? What is fx?
I think question is said uniform. No?
Question it is said uniform.
Yes.
We have
Yes.
uniform.
Yes.
So it will be uniform throughout.
Yes.
So this will be uniform throughout 0 to 3a. Correct? You can get it from here also. So this is, we have something like uniform, it said. So it will be something like 2 by 3. And fx of a is 2a, something 2a. It will get cancelled and it will be something like 1 by 3a. Okay. We have 1 by 3a in the interval 0 to 3a. Okay. So this is like, see, this is a constant value. And in this interval, whatever the y is, we have the same density. Okay. So if we have the same density throughout the y, which distribution it will follow? Uniform distribution. So this will follow uniform 0 to 3. Okay. Similarly, if I wanted to find x given some y is equals to b, this distribution. So that means this is given. So this is y is equals to b. So what will be this point? B by 3. Oh, it's already
B by 3 to 1.
B by 3 to 1. And in this B by 3 to 1, it will again be uniform. Okay. This will follow uniform B by 3 to 1. Okay. So yeah, ultimately what we have to do is you have to draw the graph first. You try to draw the graph and you try to find the region in which the probability density function is greater than 0.
So can we plug the value here also?
Can we?
Can we plug the value? Can we compute the value like in previous case? So the yeah,
Even here.
So the numerator part will be fxy. Yeah, the numerator part will be fxy x comma b divided by fyb.
We will have this as
2 by 3.
2 by 3 divided by, so just substitute b in place of y.
Yeah, 2 by 3, 1 minus y
b
by
3. b by 3.
Yeah, so b by 9.
2 by 3 of 1 minus b by 3. Right? 2 by 3 of 1 minus b by 3. b by 3.
Yeah, so b by 9 it will happen, no, sir? So okay, yeah, okay.
Okay. So this and this will get cancelled. And we will have 1 by 1 minus b by 3. In the interval b by 3 to x to 1. So you see the interval difference is 1 minus b by 3.
Yes, it's
so
matching.
1 by 1 minus b by 3.
1 by b minus a, it is satisfying that formula also.
Yeah, 1 minus b by b minus a.
Yes, it is satisfying that formula.
Yeah. So it will also follow uniform b by 3 to 1. Okay, I didn't see the time. It's already 10:50. So what we do is, so whatever week 6 we are done.
Great session.
Yeah. So we still have to. You guys requested some session for week 1 to 4, right?
Sir?
Week 1 to 4, you guys said you have lots of doubts and queries.
Yeah, sir. Sir? For next week also, sir, you please come for this concept session, sir, for week 7 also.
Yeah, I'm trying my
next
level.
Friday. No, sir, you have promised that now onwards you will be taking session for us also. Every Friday you take concept revision session, sir. Yes. It was really a great session today, sir.
Okay. So see, few things you might not able to get it, but the idea behind those things are like, if you can understand that, you don't need to mug up many things in charts.
Yeah, if it's okay with you, can I interrupt? I have not really caught as to why the joint probability is 2 by 3. Can you explain that once, please? I missed that
last one.
Yeah, the last problem that you're discussing. It has given us 2 by 3, x comma y belongs to 1. Why is it 2 by 3? Can you explain that once, please?
See, why is it 2 by 3? Because we just found the region, right? This is the rectangle region. The area of this region is 3 by 2.
Yes.
Okay. Once it is 3 by 2, and it also said that it is uniformly distributed in that region.
Yeah.
So 2D uniform distribution.
Because it is uniform distribution, it is
1 by
area.
Okay.
1 by area.
1 by area. It will be.
Got it. Thank you very much. Thank you.
It's 1 by area.
Yeah. So okay. Then we will stop today. It's already 10:50.
Did you have your dinner?
No, I will have it now. It's fine. I will have it now. No worries. But I will just try to take one more session especially for week 1 to 4. Okay, you come up with the doubts which you have from week 1 to 4. Concept related doubt or activity practice graded. I think most of them have been discussed in the session. If you have concept related doubts, concept understanding, we can have one more session. I am trying for it. Last week we have so many sessions. I didn't get the slot to book it.
Sir, we try for that, sir. But sincere, humble request is that from next week onwards, please come for concept revision.
Yes, sir. Yes, sir.
For every Friday, sir. This
That's necessary.
This is what we have been requesting, that one session should be dedicated for concept revision. So
yes, even week 5 concept revision session happened, right? I was informed that week 5 they revised the concept. Is it not happened or?
No, that had happened.
I think, like, sir, just to put it directly, we request you to take the concept session.
Okay.
Yeah, that's the
Yes,
thing.
see, already three verses are echoing, sir.
Oh, okay. Okay. Yeah. See, my saying is last session there are diploma sessions, stats, foundational sessions. Many sessions are happening. That is why I'm unable to take that on-demand thing. I didn't get the slot to book actually. So we have very limited Zoom sessions. So I didn't get the slot to book. So I'm trying this week or next week, and also this.
Our Friday session is booked session. So as per plan, every Friday we have a session.
Yesterday session itself we pushed it.
No, yesterday this is rescheduled, no?
This is rescheduled. Yeah, this is a rescheduled.
Yes, we didn't have a session yesterday, so this is rescheduled. Again, tomorrow we are going to have a session, so that will be activity questions.
Okay. Mostly I will try to take one
next Friday. Yes.
revision session, and yeah, I'm still pending to take that week 1 to 4. I will take it. I will take it before quiz 2. Okay, not before quiz 2. By next week, I will try to get a slot, and it's like an on-demand session. Okay, I cannot stream it on YouTube, and it's just like if you have any doubts, come to that session. We will discuss. Inform to other guys also. Okay.
Would you be sending a calendar invite for that?
Yeah. I think you will get
intimation. There should be some notification. No?
Yeah, you will get a notification and everything, but it won't be YouTube streamed or anything else.
No problem.
Mostly, I will schedule it in evening times only, like this, 8 to 10 or 7 to 9, sometime.
Sir, we have stopped getting the WhatsApp updates for the sessions. Like when the session started, like we were getting a few. Like it's been stopped like some couple of weeks now.
Okay, maybe even the support teams are busy in NPTEL things also. I will just remind them. See, most of the.
So the thing is that for working professionals, it works best if there's a message on WhatsApp because we can't check our emails. Even our mobile have the company names configured and all that, and we are not allowed to open any other emails. But WhatsApp, it's like how we can get touch.
See, you will get. I guess. I will just remind them to send the WhatsApp things.
That would be good.
The last question on the reorganization that you were saying of the courses, the advanced statistics would be applicable even for diploma in data science, right? If there is going to be a new course that is created.
See, these all are in words, okay? It's still being processed. Lots of things. See, if a big change has to come, it's not that easy to come.
The reason is I don't want to miss out on the ANOVA. You said ANOVA is not going to be covered in this particular stats too, so that's the reason why
I am also a bit disappointed.
Hoping to catch it. I'm hoping to catch it, not avoid it.
Okay.
Don't want to miss out because calculus already I joined in data science and I started this May. And integration somehow between the lip and the cup, it slipped. The reorganization, of course, now there is no integration